Okay, good afternoon, everyone. So let's go ahead and get started. So next week, we're going to have our project presentations. So just be prepared, right? You'll submit your presentations on Tuesday, and you'll do kind of peer presentations. I'm going to be out of town, unfortunately, but we're going to have the presentations recorded so that I can still view them and then provide everyone feedback, which I'll try and do as soon as possible. Okay, the other thing I noted that we do have some time or opportunity if there are any topics that folks want to either review or different topics that you'd like to cover. I don't think I heard from anyone. So if that's not the case, we'll plow ahead and do some other neural network stuff. But if there's anything anyone wants to cover, let me know now. Yes?
Can we go over the Disney example for the logistic regression? I don't think I understand fully.
Sure, yeah. Okay, why don't we do a quick review then? Let me grab that stuff and we'll jump back to, let me see if I can, oh, did I get it first try? Yeah, this one. Okay. So this is in regards to our kind of first example of classification, right? So the idea is that when we have something like, y equals, beta 1 x, and so on, in the case of y, if this is discrete, and specifically if there are 3 plus outcomes, then our linear method doesn't quite work, right? And so, did you want to go over the conception of?
Yeah, I don't understand when we're just doing logistic and then it switches over to multinomial logistic.
Okay, great. Yes. So in a logistic regression where there's two outcomes, right? We have this curve, right, which is from probability equals 0 up to probability equals 1 of our outcome happening, right? So what was our example? This was our Democrats win. And then remember that because there's only two outcomes, this actually gives us information about this one where Democrats lose, right? Does that make sense? So to put it simply, when we have three outcomes, you should have three different lines, right? So any single outcome has some probability of happening, right? And so maybe I have a line like this, maybe I have a line like this, and then I'll have kind of a line like this. And the sum of the probabilities for any chance that it occurs, for any individual, let's say, value of x, that's going to be what? If I add up all the probabilities. 1, yeah. So these will sum to 1 for every like vertical line that I draw. It should always add up to 1. Okay? So in the Disney example, we have 4 different outcomes, right? So let me just load this stuff in. Oh no. Okay, wait. I am in the wrong working directory. So let's move over to lecture 9 and set this as our working directory. Okay, so let's try that again. Oh, need to read in my library. All right, let me try this again. Okay, so here is so the concept, right, that we showed over here, the application to that specific data set gives prediction probabilities that I show here. Now, this is not, as I mentioned way back then, this particular plot is not necessarily accurate because we have 2 explanatory variables, right? So there's the popular ratings or vote ratings and the run length, right? The length of the movie. So you can actually imagine that these are like 3D curves, and instead we're fixing the run length to the average value, and then looking at the probabilities for each of the different outcomes. Okay. Otherwise, this would be really kind of hard to visualize. Okay. Does that make sense?
Yeah, I think it's when there's the other part where
Yeah.
range of ratings, and then you have another variable, and then
So-
instead of having 4 ratings, you have 3.
Yep. Okay.
Like another added layer to the concept.
Yep. And that, so, okay, that is just a peculiarity of this particular data set, right? So, remember that these are the probability values. So if I said you have the average run length, which is what we're fixed, and then we say, oh, what would you think is the most likely movie rating if you were like at a 3 for your rating? What would you guys say is the most likely?
Like for the G, PG, or
Yeah, GPG, PG-13 or R at 3.
the highest.
It's the highest, right? So, in fact, I could say that at 1 and at 2 and at 3 and at 4, all the way up until like 4.8 8 or something, right? And then it switches over to PG-13. So at a particular point, I'm going to predict blue because you predict based off the highest probability. And then across the range, we are always going to predict blue up until right at the end, we're going to predict green, right? And then I can do this type of thing for where I fix the rating and instead vary the runtime. And that one looked like this, right? So here, in this particular, where I decided to fix the rating across the range of runtimes, I would predict that it's red, and then I would predict that it's blue, and then I would predict that it's green, right? Depending on what combination of rating and runtime values that I'm choosing. But one thing you'll note is the purple never is the highest one. And in fact, that ends up being true for the entire space, is that purple, it just so happens that in this data set, when it gets calibrated, purple never ends up being the highest. So that's why I think the graph that you're talking about, this one never has purple, because all of the other ones always have the highest probability. Yeah. So this is kind of like the 3D representation of what we would predict at the highest like probabilities across the combinations of movie runtimes. In fact, this plot you can actually see, like, it's not a true shading. I just like literally predicted at every single point, right? And it just picks the one that's the highest. Okay, does that make sense?
It does.
Yeah. Cool. Okay, any other concepts or models you guys are interested in or want me to review? Okay. If not, if I can find my mouse, where are you? Okay, here we go. Okay, if not, we will do something a little bit new today. Let me just go back to the right working directory. Okay. We covered neural networks last time, and today what we can do is show some examples of particular types of neural networks and the applications in which they are used. There's like a lot of theory and math behind each of these, which we're not going to get into. This is more a way to, dip your toes in the water to maybe understand some of the types of neural networks and how you might, like the sort of concept behind them and how you might employ them in certain ways. So let's talk about this for a second. Okay. On this slide, I have two images. Can anyone tell me what these images are? A cat and a dog. Okay. And how do you know that? These look pretty blurry to me, like they just, blotches of color. Experience. Okay. Anyone else have any ideas? right? So, we can sharpen the image. We can change the image in other ways too, right? Um, so with something like this, would you guys still be able to recognize this image? Maybe the one on the left. Maybe if we didn't prime you with the fact that maybe it's a dog, the one on the right might be a little bit harder to tell. But maybe some of you guys would be able to see this anyways, right? So, we can alter the image in sort of many different ways. And so these are your sort of original images, right? And so I guess the concept is that there's information that you have about the image that doesn't necessarily have to be the exact image itself, right? That lets you still be able to do things like classify it as a cat or a dog. And so that's a pretty interesting property and something that can get carried forward into what we're going to talk about with neural networks. So importantly, you can think that this image is very high resolution, right? And so, but we don't actually need all of this information to do the classification, as you guys demonstrated, right? So even with a super blurry image, a reduced form of the original, you can actually still classify and characterize the image. In fact, we can do quite a bit of reduction. So here's a different picture, for example. So if you look at this, what do you guys see? No one sees it? Oh, what was that? Not a map. Oh, this might be the first year that no one sees. Yeah. Not a koala. This actually wasn't meant to be that hard, but you guys might be the first year that we don't get it. So, okay, how about this? Okay, and then the original image over here. Okay, well, so I think most of you guys got it on the second one at least, right? And so there's all this. So if I'm doing classification, right, I don't need all this information about the color and this high resolution of its fur and whatnot. Well, maybe you guys do. But generally speaking, even an outline is a pretty conveys a pretty large amount of information, and you can imagine how much less information is needed to be sort of transferred in something like this compared to a picture like this. Okay, so we're going to keep this concept in our minds as we walk through the first model that we're going to talk about today. All right, so what are we going to talk about today? So the first thing is the convolutional neural network, also known as a CNN. So this is a class of deep neural network. This is essentially a regularized version of a multi-layer perceptron. And what these are good at, so this is particularly suited to analyzing grids of data. Okay. AKA image. It doesn't have to be just images, but that is a common application point, especially for classification. So let's think about, so consider, say I have some kind of picture here. Okay, you're gonna see how great my art skills are over here. Okay. Okay, so we have, does anyone know what this is? A bird? Come on, it's not that bad. Okay, so we got a picture of a bird. How do I go from like a picture into information that like a neural network could process? What do you guys think? Any ideas? What is a picture? Yes.
Collection of pixels.
Okay, a collection of pixels. Great. And what would a pixel be comprised of? Anyone know? Yeah.
Is it a set of bits?
Yes. More, I guess more specifically in one pixel, what kind of information is contained with
RGB.
yes, RGB. So if you mix colors together, right, you can essentially display a particular color. And so the image is just lots of these pixels that have different colors all stitched together into, this one picture. So I can decompose this into 3 grids, right? So you have, something like this. Oh, I didn't make them even. Okay, we'll go like that. Wait, yeah. Okay, and then I would have all these like numbers in here, right? And then each of these grids would represent the channels of color that correspond to each individual picture or individual pixel of the entire picture. Okay. But even consider a relatively small picture, right? So, actually, I don't know if you guys can see this, but right there are these little dots here. That's just kind of used as the grid. Even with only the ability to display pixels at a low resolution, you're talking about a pretty large neural network, right? Because each pixel would represent a node. And if you interconnect all the nodes, even if I were to have what I just showed here, this is a 4x4, so that's 16 pixels, which is a tiny image, right? So 16 pixels times 16 times 16. You have too many weights for a multi-layer perceptron. And that's why some of those data reduction techniques become very important. And reducing everything to an outline can still preserve the right information that you need to do the classification correctly. Okay? So we have this problem where even small images are going to make the neural network way too complicated. So we need to do some processing. So we will process images with 3 techniques. So one is a convolution layer. 2 is a pooling layer. This is known as the convolution process. And then we have a fully connected layer. Okay. So let's draw a grid. Looks something like this. I'm going to do a 5x5. And I'm going to put in some values here that we'll need to demonstrate this example. So just assume that these are essentially the pixel values. We won't worry about the different colors. Let's just assume that you can represent them as one grid for now, and we'll revisit the RGB channels a little bit later, right? But essentially what you're saying is, oh, I have some information about my image that I can represent in this grid. Okay, so we've got this 5x5 grid that is our original image, and let's say we want to reduce the amount of information being passed to our neural network. How can we do that? Let's do something like this. Okay, first thing we're going to learn about are filters. And this is our first filter, one of the simplest. So this is known as a mean blur filter or a kernel filter. or also known as a kernel filter. So if I apply this filter to this grid, what I'm going to get is something like this. So the first value will be 41.6. Okay, and how did I get that? So the idea is the application of this filter to my original grid looks something like this. I'm going to I am going to take all of this information. It's going to be 20. So it'll be this value times this value plus this value times this value plus this value times this value, and so on and so forth. And basically, I'm going to average everything. And so if you take the average of everything in this square, you end up with 41.6. Okay? And let me fill out the rest of this. So this will be 58, 61, 41.8, 63.8, 70.3, 45.7, 62.1, 67.1, right? And it's the same thing. This second one is the average of those values, and so on. Everyone following along? So now, image is smaller and blurrier. Okay? There's the smaller part you can alleviate by padding. So if you wanted to retain the original size of the image, you could pad the outside. Okay, and so this has something known as stride, which is the number of steps in a direction. So the filter applied to this original data would have what stride? So it's 3, right? Because you have 1, 2, 3. It moves in 3 steps across the original data. Okay, so we'll remember that for later, but right, the application of this filter will blur the image essentially by sort of averaging these 9 by 9 pixels into 1 pixel with an averaged value for its color. Okay, so that effectively blurs your picture. What are some other types of filters? So we have something known as an edge filter, of which there are a couple of different types. 1, 1, 1, 0, 0, 0, -1, -1, -1. You have So this is known as a vertical edge filter. 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. This is a horizontal edge filter. You have something like this. This is known as a Sobel edge filter. And then similar in principle. You have something known as a Char edge filter. Okay, why are they called edge filters? Let's take a look at how these work. Let's say I apply this to a larger image. Okay, so let's say this is an image. That looks something like this. Okay, so what would this image look like? You basically have the 6 by 6, there's 10s on one side, 0s on the other side. Essentially you have like a 2-color image. This might be, for example, like you've zoomed in on the cat. And this is the cat, and then this is the like background, right? And so this is like the border of the cat, which is like one color. I colored it blue, okay, but maybe it's okay, maybe we'll do it like this. Maybe it's a black cat standing in a field, okay? And this is kind of just zoomed in. So you can imagine it looks something like this. So if I were to apply this edge filter using the same rule that we did before, what would that look like? So this is going to get reduced down to a 4x4 matrix. Okay, so we'll do the same thing here. What's 1 times 10? What's 0 times 10? What's negative 1 times 10? Okay, so you have 10, 0, negative 10. What's the average of those three? 0, right? So here, this would be 0. I can do the same thing for the middle ones, and you end up with something like this. I guess here I'm taking the sum and not the average. But the idea, I mean, even if you were to take the average, it'd be 30 divided by 9. So the idea is now I've gone from black cat, green field into just the border between the cat and the field, right? And so that's how you create an outline, is using a filter, using these edge filters essentially, okay? Any questions? Everyone's following along? There's a couple other filters that are pretty common. So sharpen looks something like this. You have, 0, -1, 0, -5. And we have Gaussian blur, which looks like this. 1, 2, 1, 2, 4, 2. Okay, so bunch of different filters that you can apply to an image to help reduce it. So in our neural network, remember we have this sort of generic form right? So these in our feed forward, these are our weights. This is our activation function. And then here we have our input. So the filters in CNN, these are our weights. Right? And so remember, the weights are calibrated in such a way that we reduce our error as much as possible. And so here, you're basically saying, oh, I'm gonna like put this image through different filters in such a way that I can still classify the images correctly, right? Which is essentially our error. And so the neural network will essentially decide how much it wants to trust in different filters. I don't know if trust is the right word, but it'll choose how much to weight different filters that you can apply to your image such that you can still maximize its ability to do classification. Okay? For the activation function, typically in CNN we use the ReLU. So this helps with computation of the gradient. Either ReLU or similar types of activation functions. Okay. Any questions? Yes.
Are you applying like multiple filters to a picture? Is that like very common? Like,
Yep.
pair of?
Yep. I will show in a moment like typical ways of setting this up. And essentially, you choose a handful of filters to apply to an image, and then the neural network is going to decide like which of those filters are actually going to like which filters are like the most important to retain information that you can use for classification. So I might use something like I'll just like throw 5 filters at it and then let it figure out the weights.
And then at the end, does it know like to like keep that data that was like kind of like averaged out in the end, I guess?
That would all be information that's like in the hidden layers, right? Because all the transformations are happening inside of your neural network. So you could go in and figure out like what the filter is specifically doing to your image, but for the purposes of like what people usually use the model for, it's just like throw some filters at it, let it figure out the weights to like let it do the filtering in the way that it thinks is the most effective, and it gives you this model, and essentially all you really care about is that it gives you the best prediction possible. So like anytime I feed it like a new picture of a cat, it'll be like, oh, that's a cat, that's a dog, that's a motorcycle, whatever, right? So that makes sense. So yeah, I guess it is possible to go in and figure out like what information is lost, but people don't often look at that. Yeah. Any other questions? Okay. So that is the convolution layer. The next thing is pooling. And pooling usually looks something like this. Okay, wait, hang on. I'm realizing I made a slight.
Is it normalizing?
Sorry?
You gotta normalize the filter?
No. Actually, I misspoke with, sorry, I confused myself with stride. What you were saying was correct. I was wrong, or I had a brain fart. So stride is like the size of steps that you take when you apply a filter. So here we're doing 3 applications across the data, which means that you're taking it in step sizes of 1. So what you were saying was correct. So basically that means if I apply a filter with a stride of 1, it's going to apply to the first spot, then it's going to take 1 step and apply to the next one, and then 1 step to the next one. So the total number of steps that you take is 3, but it's a stride value of 1. Okay. And that's going to come into play here with pooling. So with the filters in the convolution layer, what I was saying is that we're applying this to reduce reduce the image in a certain way, right? We're like blurring it, or we're like doing something like sketching out the outline. But actually, especially if you do padding, the size of the image actually doesn't really change, right? So you're still blurring, but at this like kind of higher resolution. And so pooling is the step that actually reduces the size of the image. So here, I would maybe reduce this down to something like this. So 9, 2, 6, 3. Okay, so what's happening here? 9, 2, 6, 3. I am still actually applying a filter. Okay, and so what filter am I applying here? Yeah, the max. So it's going to look a little bit similar, but the properties here, so one, we're going to look at our filter size. Two is the stride, and three is the type. And so oftentimes you're doing max or average pooling. Okay? So in this particular example, this is now a stride of 2, right? Because we apply the filter, then we move over 2 steps in each direction. So this stride equals 2. And the filter size is a 2 by 2. And so this reduces down from a 4 by 4 into a 2 by 2. So the convolution layer, the purpose of applying the filters is to reduce the information in the original grid. And the purpose of the pooling layer is to reduce the size of the grid. Okay. So when you're applying something with a stride of 1, right, you reduce the edge of the image in size unless you pad. So that's not really going to decrease the amount of information that much, especially if your picture is really big. But when you apply a larger stride size, that will reduce the size of the image a lot, right? And so with a stride of 2, we're reducing the size of the image by a factor of 2 in each dimension. If you had a stride of 3, you'd be decreasing the size of the image by a factor of 3 in each dimension. Okay? Any questions? So those are our first 2 steps, the convolution step to apply filters to reduce information, and then 2, pooling to reduce the size of the image. And then the last step is flattening. So converts last convolution layer into a one-dimensional neural network layer. Okay, so I would take my 9263 and I would flatten it out, and those would be like inputs into my like flattened out neural network. So why would we do this? We have all this information from each of these steps. Why not just fully connect all of the layers, right? So why not fully connect all layers? And this is because the number of weights grows exponentially. Plus all of the parameters that you have. So to demonstrate this, let's consider a very small image. So consider a 32 by 32 pixel image with RGB channels. So we have our convolution layer. Let's say we have 5 filters, 1 stride, and then we have our pooling layer. So this would be, let's say, 2 filters. You could do both the max and the average, and let's say these are at 2 stride. So just the first input and first convolution layer would have, okay, so what would be the size of our one image as just like an input into the neural network? In a 32 by 32 pixel image, how much data would that be? Or how would I write that out? Any ideas? So it's 32 times 32, right? So that's how many pixels, individual pixels there are. We have like about 900. And then we have one for every color, right?
Quick question. So for image classification, how come it needs to be RGB and not just like grayscale?
You could do grayscale. Yeah, so that's a filter that you could actually apply to reduce the size in like pooling, for example. So yeah, you certainly, so this is more to demonstrate why we don't try and preserve all the information and pass it into the neural network. So with just the image, you would have 32 by 32 by 3. So you would have 900 and then what, 2,700-ish nodes as an input, just from the original image. And then if I were to include the convolution layer, right? So with 5 filters, each one reducing the size, you have what, 28 by 28 by 6. Okay, so oop. So if I wanted to take all of that information, the original information and all the filter information, and just shove it into a neural network, just with the convolution step and the original image, you're talking about on the order of 14 million nodes, okay? So very impractical to try and pass all of the information through the neural network, right? And the whole point of this was to reduce the information anyways. So what does that look like? So instead, what we do is, okay, we have our 32 by 32 by 3 input layer. We apply 5 filters at 1 stride. Maybe that will reduce down to something like 30 by 30 by 5. So this would be our first convolutional layer. plus relu plus the activation function. And then let's say we apply 2 filters at 2 stride here, right? This would decrease the size by half. So this would be something like a 15 by 15 by 10. So this is our first pooling layer. Then you could, in theory, do this again. And what you'd end up with after you flattened it, right, you could continue to reduce until you have the critical amount of information. You might have something like, 400 node input layer. Going to your output. And this stuff would be fully connected. So every node would connect to every other node and so on. Okay, and the classification, often we use something like a softmax. So this goes into a single node for our classification. Softmax, yeah, we don't need to know this, but this is something like this. Maybe this looks familiar, right? This is a generalization of logistic function. Oh, I wasn't even saying this right. 30 by 30 times 3, that's 27,000, right? So consider that a tiny 32 by 32 pixel image has essentially 27,000 bits of information, but we might only need 400 bits of information that we filter out of that image to be able to do a good classification. Okay? And that's kind of the power of the convolutional neural network. So I'll show an example of this in the code. And yeah, this will be one of the instances where you don't need to necessarily type along. There's a decent amount of code here to do this, and some of these packages take slightly longer to install. They're not that hard to install, but maybe right off the bat we wouldn't do that. And so what I'll do here instead is walk through the code, and then obviously I'll provide this as reference for you guys to look at later. Yeah, so there's some more complicated stuff kind of happening behind the scenes. The reason why these packages actually tend to be a little bit more complicated is oftentimes the parallelization of running some of these uses specific settings to, like, in some cases use your GPU, and it may be kind of specific to your processor as well. So that's why it's a little bit less straightforward. But here we go. So loading in some of these packages, and actually some of the base of some of these are originally in Python and C, and kind of modified to be able to use in R. So they operate a little bit differently, but okay. there's this famous data set in convolutional neural networks that is commonly used as an example. And so I want to show you guys what that looks like here. Okay. Before I talk about the image directly, there are a whole bunch of images. We just grabbed the first 30. And these are showing images of these different things. So airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So these are 32 by 32-bit images. So there's 32 pixels horizontally and 32 pixels vertically. And so maybe you guys can make this out, right? So number one would be a... Yes. I was going to say, you guys got to work on your image classification. Number two, truck. What is number four? Did we have sheep? We don't have sheep. I'm guessing it's a horse. Okay, so horse, car, bird, horse, boat. Okay, and so on, right? So these are already fairly low resolution images. And we can apply, so you can see in this code how it is doing some of the filtering and pooling, right? And so here there's actually 32 filters, 64 filters. It's looking at the pooling size. This is the filter size and the stride size. So this is our model that we can run. And okay. So you'll see, after you do all kind of the setup, right? So in terms of applying the filters and the pooling and then flattening it, and then this is line 38 is setting up the model options, and then 41 is actually running the model. So fit is the function that will actually run everything, and it does take a little while to run. What it is doing is, so we built out the neural network and it's iterating essentially to figure out what the right weights are for applying the filters, and it's doing, I fed it both a training and a testing data set, and it's looking at the sort of value loss. And so we talk about different ways of scoring the ability of the model to do well, right? And so, something like a mean squared error in a continuous one, error rates in models that have discrete values. So there's a particular loss function that it's using here, and it's going to continue to iterate until it reduces your out-of-sample test errors kind of as much as possible. The algorithm happening behind the scenes is very much going to do essentially what we've always been talking about, right? Which is this like bias variance trade-off. It's going to refine the weights, put a lot of the filters on, take the filters off in a smart way, such that it figures out what my total error rate looks like, and it's going to basically choose the lowest one. And that's going to essentially replicate this technique, right, that we've been doing throughout the class of reducing bias against the overfitting variance portion of it. So it's plotting, over the sort of iterations, what these loss values are doing. Okay. So yeah, ultimately you essentially end up with this like model that's calibrated that you can throw in new data to do sort of additional classification. With where the model ends up, there's not too much to show. The like neural network, the actual what that network looks like isn't all that interesting for us, right? It's not like we can infer anything from the network. Really, what we care about is its ability to do predictions accurately. And so, having trained this model and then passed test data to it, test data being images that it didn't train on, how well does it does? Well, it has an accuracy of 65%. Okay, so if I were feeding it, if I were to continue feeding pictures of it, it would get more than half of them right. And so, is that a good model or bad model? I guess that's kind of up to you and your context. But yeah, pretty impressive, right? It can like essentially take an image and figure out what it is based off of information that we've passed it about other images before. Okay? So that is a convolutional neural network. Any questions? Okay. Yes.
Sorry, just back in your written notes.
Yep.
You just like visualize again like what the stride is. And what
Yep. Okay, here. So stride is, I have a filter and I apply it to some data. So this filter, I'm applying it to this data here. Okay, and so then I figure out what the value is, and that's all good and fine. The stride tells me in the next step, when I apply the filter again, how many steps do I take in a direction. So with a stride of 1, it's going to walk over from here. It's going to go from here 1 step over to here. I don't know if you can actually see that, right? So it takes 1 step over. And so usually in the convolution layer, you are doing stride of 1 so that you apply the filter in 1 step every time. But in the pooling layer, when you're trying to reduce, right, you can see I didn't go from here to here. I went from, I went from this one to this one instead of this one to this one. Does that make sense? So that would have a stride of 2. And so if you...
But it doesn't say anything about the size of the filter. That's just the...
Yeah, that's right. That's right. Yeah. But the stride will go a long way to like decreasing the overall size, right? Okay. All right, any other questions about CNNs? Okay. So that is an example of a neural network that is designed specifically to essentially take information that you have in these like large grids and reduce them down into something more digestible. Right? We always talk about how neural networks are really good at handling large amounts of data. So that's a sort of practical example, an application of a particular type of neural network that is able to digest these like large grids. And so the next one I want to talk about is a recurrent neural network. So we had CNN, and now we'll talk about an RNN. And so this is a class of artificial neural network designed to process sequential data. Okay. So whereas CNNs are really good at these large grids, RNNs are really good at sequences of data. Where is that very common? So time series, right? That's probably the most prevalent sort of data structure that thinks about things in sequences. So let's consider each time step is a feature. What if the sequence is 1,000 steps? What if sequence has different lengths? What if patterns shift in time? So these are all features of time step sequences that might arise in your data set. And consider the two types of networks we've talked about so far. So feed forward and CNNs. Assume fixed size and independent inputs. So both of these guys would be kind of not great at handling sequences, right? Because one, your sequences might not be fixed size, and two, they're definitely not independent, right? You're basically saying something in the past is influencing something in the future, and so you have this. Let's say xt plus 1, xt plus 2, these going in to your hidden layer, but these might be connected in some ways, right? And so that's not really represented in the way this is structured. So how is an RNN structured to deal with this? Okay, so let's think about our original neural network structure. So that looks something like this, right? So we have x1 going into a hidden layer. We have all of our activation functions. We'll do something like this. Going to y1. So we'll say this is let's say this was t equals 1. So this is our hidden layer. We'll call this h for now. And we have weights, so this will be w x h, and this will be w h to y. Okay? Hopefully pretty familiar, right, from last lecture. I'm just kind of putting the hidden layer generically all together. Okay, and so this is our basic structure of a neural network. And just as a refresher, okay, I'll also say we're going to assume activation function is tan h. I'm not going to get into this. There's certain reasons why in RNNs tan h is a very common activation function. So we'll just assume that A is tan h in this example. Okay, and so as a refresher, right, so our hidden layer would then be, tan h with all of our weights, xt plus, I'm going to use b, but this is our epsilon error term. Okay. Everyone remember this from last class, hopefully. We had A here instead of tan h, but now I'm kind of pre-selecting our activation function for us. Otherwise, these are our weights that we have to calibrate. That would have been like the betas. That analogy would be like the betas in our original linear regression, right? Okay, so look something like this, and y of t is equal to something like this. So same thing. And if you wanted to, you could like plug it in, right? So w h y, then it would be times tan h of w x h x t plus b of h plus by. Okay, that would just be plugging this thing into here. Okay. So this is like basically a slightly reformatted version of the feed-forward neural network that we looked at last time. And now what I'm going to do is I'm going to modify it a little bit. And the reason why I want to do this is if we have a sequence of data and we're assuming that there's some information about a particular time step that you want to get passed to the next time step, you need that information to propagate in some way. Whereas, if I were to set this up as x1, x2, x3, right, as I was just saying, we don't have any information about here getting passed to the next time steps. So we have to restructure this in a little bit, in a slightly different way. So I'm just going to reorient this. Just a little bit. So I'm just going to put the x's and y's at the bottom and top here. So this is t equals 1. So we have the same thing as over here. So this would be wxh. This would be why. And we still have our stuff here. But I'm gonna have some other information that looks something like this. And this one will have a weight WH, and we'll have something like this, okay? So these are gonna be hidden nodes that contain information that gets passed into the like processing step for going from x1 to y1, and then that information is going to continue to sort of propagate down. So what would this look like in terms of the equation? Right, all we're doing is we're modifying this to add an extra term. And then y of t is going to end up looking the same. So now, maybe you can imagine what we're going to do here. I'm going to take the information in the hidden layer from the first step, and I'm going to pass it to the next step. So in this diagram, this will be at time step equals 2. We'll have our new hidden layer. Which now sees information from the previous hidden layer, and it will continue to pass this along. Right, and so you can imagine this continues and so on, all the way up until however many time steps we have in our sequence. Okay. So essentially what we have now is separated out time steps. You've kind of unrolled everything so that you can see how hidden layer information is passed to the processing of each subsequent hidden layer. So each hidden layer depends on the previous hidden layer in the sequence. Note, very specifically, WH, the weights, WXH, WHY are the same at every time step. So it's the HT that is the memory. Okay, the HT is the thing that contains information that gets passed on to each subsequent step, the hidden layers, I should say. The weights are the same in every time step. Okay, any questions about this? Okay, there's a lot of configurations of this, so I'll just maybe note that here. So many configurations possible. So you can have many to one, one to many, and then many to many. This is a sequence input and a single prediction out. This would be a single input with a sequence out, and then this would be a sequence input and a sequence output. And there's two types here. Aligned is same length, and it's called encoder decoder. This would be different lengths of sequences. Okay. Let me actually, I think these actually take a little time to run, so give me a second. Let me actually run this while we talk. Okay. Any questions so far about the RNN? I'm going to talk about one more important concept with the RNN, but we're not going to have time to show this kind of solution, but maybe I'll just talk about it and we can wrap it up next class. So there's a particular problem with the application of RNNs in certain contexts, and this is commonly known as the vanishing gradient. So as you recall, right, when we switch to kind of machine learning, the way we solve for the weights or like the betas, right, with these sort of larger scale problems is to use a gradient descent. And so that's no different here. So RNNs are trained using gradient descent. Okay. So recall what this means, right? So I have a bunch of weights, right? In the linear regression, your weights are your betas, and you have an optimization that you're doing where you want to reduce the size of your errors, right? So you, essentially the way that this works is you're taking, gradient descent takes a step in a certain direction based on the derivative, which is like the slope, the change in your loss value. In the linear regression case, that would be our residual sum of squares. And it's adjusting your betas until you arrive at a point where the loss function is minimized, right? So, or your total sum of squared errors is minimized. And the gradient is essentially that derivative piece of it, right? And so the step that you take in a particular direction is informed by how much you're improving on your loss score. But in these cases, you have dependencies with long sequences. Right, so h of t, our hidden layer, depends on h of t minus 1, which depends on h of t minus 2, and so on and so forth, right? So what does the gradient look like? So the gradient loss looks like something like this. Because of the dependencies, oops. Because of the dependencies, the gradient depends on essentially the slope for every what's the opposite of subsequent? Previous, for every previous hidden layer. So without going into the math of this, imagine each term, each change in loss term is, let's say, 0.4. So after 10 time steps, then you have 0.4 to the 10th, right? So this would be approximately a change in loss of 0.00001. After 20 time steps, you have 0.4 to the 20th. That's 1 e to the minus 8th. And then after 50 time steps, you have 0.4 to the 50. That's approximately equal to 1 e negative 20. So the concept of the vanishing gradient is that our network can't tell if changing h would help or hurt at step 50. So there's this kind of nuanced problem where my ability to do that optimization, to minimize or maximize something, because of these dependencies, a small change in the hidden layer at time equals 1, you're not going to be able to tell what happens at time equals 50. You actually have the opposite problem too. So you have a vanishing gradient and you also have an exploding gradient, right? Because they're so interconnected, if your loss function changes a lot in each time step, then it could explode. That's less of a problem in this in RNNs because of the 10H activation function. You can actually set a cap to the amount of change that can happen in your loss. Yeah, it's one of the reasons why it's one of the activation functions chosen. So the solution to this is to actually cap how far forward you're looking in any particular sequence. And so that's a modification of the RNN, which I guess we won't have time to talk about today, but that's is known as LSTM. This is long, short term memory. So I'll briefly talk about this at the start of next class to show us what that looks like. Okay, cool. So jumping over here, same thing. There's a lot of code here, so don't necessarily need to follow along. It's going to use the same package, Keras, as what we had used before. I set up some data. Oh, let me get rid of all this. Yeah, so I set up some data where we have a synthetic time series data. Looks like this. The way that this works is you build out sequences of training data. So I'm going to build out sequences. So I have 50 time steps, but I'm going to have a sequence of 30 look back steps. And so essentially the training data will be from like 0 to 29, and then you predict what happens at 30, and then 1 to 30, and you predict what happens at 31, and then 2 to 31, and you predict what happens at 32, and so on and so forth, right? So we should have something like 20 bits of training data. I split this out into 80% training, 20% testing. This is kind of the same setup or similar setup to what we've been doing before. And then I arrange the data in a particular way based on what Keras wants. Okay, so you can read my notes on this before. Okay, and there's not much to see here in the summary. Here it tells us how many parameters that it's training. But like I said, the parameters that are determined by the RNN is not very useful, right? We're like so far out of the inference realm that we're not really going to bother even looking at what the structure of the neural network looks like. Really, the thing we care about is prediction. Okay. So this code actually runs both the normal RNN and an LSTM model, which we'll talk about next time. And I guess I'll just show you. So this is that loss function as I train the model over time. You can see what this looks like, and you can see the comparison of the RNN and the LSTM. I'll talk a little bit more about this comparison next time. I think the main thing here is to show you guys, yeah, don't worry about the LSTM prediction yet. So here, this is our test set. If we look at the actual data, that's in red, and then our RNN data in blue. And you can see how well it does in kind of fitting to this sequence. You can compare this against some of the like time series models that we had used before, but generally these are very, very powerful at predictions, as you can see here. Okay, and so we'll end here, and then we'll pick up with the LSTM to close out next time, and then we'll do kind of a review of the course concepts next class. All right, that's it for today. See you guys on Thursday.